Yeah, thanks for that. Hi, everyone. So yeah, I'm Mathias, and I indeed work for Opera Software in developer relations. And today, I'm about to make you hate performance, because usually when we talk about front-end performance, we see it as a good thing, and usually it is. But today, I'm going to focus on some security-sensitive situations in which performance can actually be a problem. I will also demonstrate that some new and performance-related web APIs can sometimes cause some security issues. They can have a negative security impact. So let's get right to it. Here's a simple example. Let's say you want to compare two strings in JavaScript. It's not very tricky or hard, right? You would probably just use an equality operator, and because you're just comparing two strings, it doesn't matter whether you use triple equals or double equals, so let's just bypass that whole discussion. Okay, you compare the string ColdFront with itself, and it returns true. And if you compare two strings that are different, it returns false. This is exactly what you would expect, right? Well, I promised I would talk about performance, so let's get some timing measurements up in here. So let's say the first example where the two strings are equal takes up about 1,000 microseconds to run. The second example where we compare ColdFront with a T at the end with ColdFront with a D at the end also takes up about 1,000 microseconds. However, if we compare Pikachu with Pichu, we get the result much more quickly. It only takes about 100 microseconds. And if we compare the string CSS with XSS, then suddenly we get a result in 200 microseconds. So there's a lot of differences as to how long it takes for this function call to complete, depending on the input strings that we feed it. So why is that happening? Well, the answer lies in the way that the JavaScript engine or the engine of the programming language that you're using, because this is not specific to JavaScript in any way, it lies in the way the engine implements the equality operator for these strings. So just imagine how you would be implementing this if there was no way to compare two strings directly. Well, there's only really one way to do this. You would have to loop over the string character by character, get the character code at each position, and then compare it to the character code in the other string at the same position. And if all the character codes are the same, then you know the strings are equal. And as soon as you start writing that out in actual code, it will become really obvious that there are some performance optimizations that you can apply. So let's take a look at some code here. So we have our loop right in the center of this slide, but before we even get to the looping part, we can already apply an optimization. We check the length of the input strings, and if the length is different between the two strings, we know that the strings can never be the same. So at that point, we can just return false right away, and this is called an early exit or an early return. That way we avoid doing any more work and we bypass the loop completely. Now, another performance optimization takes place in the loop itself. As soon as we find a single character code that differs between the two strings, we can break out of the loop and return false right away. We don't need to check the remaining characters anymore because we know there's at least one difference between the two strings. Now, in terms of performance, the absolute worst case is when the two strings are equal, because that means you have to complete the entire loop and compare every single character, and only at the very end you know for sure that the two strings are the same. And that's when you return true. So with that in mind, if we look back on our earlier results, it kind of makes sense. It's clear that there is a difference in runtime performance depending on the input for these functions. So if we compare ColdFront with itself, we have to complete the entire loop before we can return a value, the value true in this case. If we compare ColdFront with a T at the end with ColdFront with a D at the end, optimization number 2 kicks in, but because it only applies at the very end for the very last character in the string, there's not much of a performance gain there. Comparing Pikachu with Pichu is really fast because the length of both these strings is different. So we just return false right from the beginning and we don't even enter the loop after that. We don't even have to compare any character codes at all. When we're comparing the string CSS with the string XSS, the second optimization kicks in once again, but this time it does give us a very nice speed advantage because the very first character of the strings differs already. So at that point, we just exit the loop and return false right away. We don't have to keep on checking the remaining characters. So what's interesting here is that we're not just getting a Boolean result of true or false, which is what this function was designed to do in the first place. We can infer even more information just by looking at how long it takes for the function call to complete. And this is what is known in the cryptography world as a side channel leak. And because the side channel that is actually leaking information in this case is the timing measurement, you could say that our compare function is vulnerable to a timing attack. Yeah, so a timing attack is like going to the restroom at a dinner party, because depending on how long you're away for, people can kind of figure out what it is you've been doing in there. So getting back to our comparison function that is vulnerable, well, usually it's not that much of a problem. If you want to compare two strings, you want this to complete as quickly as possible, right? And that is true as long as you're comparing data that isn't supposed to be secret. The problem starts when user input is being compared with some hard-coded value that is supposed to remain a secret, like a password or a hash, for example. And this happens because each and every one of those performance optimizations that we implemented earlier is now a weakness. The first optimization, where we exit early when the length of the two strings differs, this allows an attacker to figure out the expected length of the secret string. All they need to do is just try some inputs of different lengths, while measuring how long it takes for each function call to complete. So the attacker could just send one character, then a string with 2 characters, then 3 characters, and so on, and they would time how long each operation takes. And as soon as one of those input strings results in a slightly longer runtime than all the others, you know you have found the correct length. So once you know the length of the secret string, you can start brute forcing the characters within the string. So you create a string of the expected length, and then you start brute forcing the first character. You try A, then you try the character B, then you try the character C, and so on. And once again, the attacker times every operation that they perform. And if one of the input strings results in a slightly longer runtime, it means that we probably end up in the next loop iteration. That's why it takes a little bit longer. So that means that the correct character at the first position is found. And at that point, the attacker can just repeat this for the next character and the next character and so on. So the attacker cannot use a timing attack to figure out the very last character, because at that point you either return true or false, and there is not much of a performance difference there. But at that point they can just try every possible combination for that last character, because it's only one character that they're missing. So how can we avoid this problem for the compare function? Well, whenever you're comparing sensitive strings, you should use a safe comparison function. And here's an implementation of that. This is a constant time comparison function. How do you create such a function? Well, you basically undo all those errors. You try to make sure that the code executes the same number of instructions, of operations, regardless of the input. So here you see that I'm still comparing the length of both strings at the beginning, but instead of just returning early, I'm storing a flag in some variable. And then I still go through the entire looping process, even though I know it's not really necessary to get the result that I'm looking for. The goal is to make sure that the function takes about the same time to complete for any two input strings. Okay, so this was a very generic example of a timing attack. And at this point, you're probably wondering how front-end web developers can execute timing attacks against their visitors on the client side. So I'm going to show you this in just about a minute, but first we need to talk about an old privacy problem on the web. CSS has a visited pseudo class that enables you to style links that have been visited by the user before in a different color or with a different background or things like that. So in this example, all the links on the page would be green, but the links that the user has visited before would have a red color instead. I'm sure I'm not telling you anything new here. But a long time ago, in a galaxy far and far away, back in 2009, some clever people discovered a way to figure out someone's browsing history using nothing but HTML, CSS, and JavaScript. So what document throughout the visit. So when and at that point, this data can be used by the website to fingerprint the user and to basically reconstruct their browsing history. Because this simple technique could be performed for thousands of URLs per second. It made it possible to figure out a sizable portion of the victim's browsing history or to even uniquely fingerprint the user. It was a huge privacy problem. And not just in theory, by the way. Research showed that this technique was actually being used in the wild on various popular websites, mostly by evil advertisement companies, let's say. And as a result of this, web browsers ended up making some changes to their implementation. And as a result, if you try this today, you will find that document.querySelector actually lies to you. And it pretends that the user has never visited any website before. So if you use the visited pseudo class in querySelector, it won't give you any results. Now, of course, this particular attack is an attack, but it's not a timing attack. I should state that. There is another way of performing the same kind of thing, which was also discovered around the same time, and that was to use the getComputedStyle on the links. So you display the same list of links, you get the computed style, and then you read out the rendered color for each link. And then the script differentiates the visited links from the non-visited links just by looking at the color, just like a human being would. And that way, you can effectively still figure out which of the URLs the user has visited before. And as a result of this, browser vendors ended up changing getComputedStyle and also made it tell white lies. It now pretends that the user has never visited any website before. And once again, this is also not a timing attack. And also, this technique is very old, like I said, and it hasn't worked since 2010, when browsers started protecting against it. So why am I still talking about it? Well, I just wanted to establish that it's really not supposed to be possible to leak a user's browsing history like that. And in fact, browsers jumped through all kinds of hoops to try to prevent people from doing so. And then in 2013, a researcher named Paul Stone came up with a new technique that bypassed these browser's protections. He observed that links are re-rendered whenever their state changes from non-visited to visited or the other way around. So for example, when the user clicks a link, at that point, the link becomes visited, so the color changes from blue to purple, for example. So Paul also realized that a link's href attribute can be updated dynamically by using JavaScript. So what you could do is you can create an HTML link and point it to a fake URL on a domain name that doesn't even exist, so that the user likely won't have visited this URL before. So this way, the link is rendered in the non-visited state. Then you update the link's href using JavaScript to some other real URL that you want to test. And if the user has visited that URL before, then the link is re-rendered in the visited state. If the user has not visited that URL, nothing changes, no re-rendering takes place. So with that information, the only thing missing to still steal the browser history is a way to detect whether such a re-rendering event has happened or not. And Paul, of course, found a way to detect when these re-renders happen. And here's how he did that. He applied some computation-heavy styles, such as the ones you see there, like a text shadow with a massive blur radius. And by doing that, he managed to slow down the rendering of all links on the page until it could reliably be detected using JavaScript timers in request animation frame. So if a given URL causes a re-rendering, it means that the user has visited that URL before. So he used request animation frame, and every time he was given access to a frame, he would just get a timestamp, and then he would compare that timestamp to the previous frame. And by looking at how long it took for the one frame to advance to the next frame, he was able to figure out whether a re-rendering took place in between these two frames or not, because he slowed it down badly enough. So this is 3 times essentially the same problem, but this time it has been solved using a timing attack. And timing attacks are in general just a little bit more, harder to defend against from a browser point of view. And here's a very modern timing attack. It's called Sniffly, and it was discovered by Yan Su. And here's the demo page. It doesn't look super fancy, but it's another timing attack that detects the victim's browser history. Out of a list of domains, Sniffly is able to figure out whether the user has visited a link on that domain before or not. And here's how it works. So for each domain that Sniffly checks, it starts a timer. Then it loads an image on that domain over HTTP. So not HTTPS, but just plain HTTP. All of these domains in the list, they use strict transport security, which means that if the user has visited that site before, the browser will rewrite that request automatically into HTTPS. If the user hasn't visited that site before, no such rewrite will take place. Now, CSP, or Content Security Policy, is being used on the Sniffly website to restrict images to HTTP only. So images are blocked before they are being redirected to HTTPS. And whenever an image gets blocked by CSP, the error event fires. At that point, the timer is stopped, and Sniffly now knows how long it took for the image to be redirected from HTTP to HTTPS. And then you just look at how long it took. If this time is on the order of, say, a millisecond, then it was probably an HSTS redirect, because no network request was being made. This means that the user has visited the image's domain before. Now, if this timing measurement is more on the order of, let's say, 100 milliseconds, then it's very likely that a network request occurred, meaning that the user hasn't visited that image's domain before. So I thought this was a very clever combination of different relatively new techniques on the web that still allowed us to invade users' privacy. And these attacks that we've seen so far, they're all kind of nice, but they're also maybe a little bit complicated. So let's simplify things a little bit just for now. What does the simplest possible timing attack on the web look like? Well, it looks something like this. Here's some very simple code that performs a very simple timing attack in the browser. First, you start a timer, and then you load an HTML document as an image. Now, the browser will try to parse this HTML document as an image, and that will fail because, in general, HTML documents aren't valid images. And when that happens, the error event fires. Now, as soon as that happens, that's when you stop the timer, and then you can log the results. You can compute the difference between the end of the timer and the first timestamp that you had. And by filling in the blanks, the function will look something like this, which is really not a lot of code. It's still fairly simple. So this timing attack gives you an idea of how long it took for the user to download a particular resource, and it could be used for any URL that is not an image. So how is this useful? And how could evil people use this against you? Well, imagine that a given URL returns either a very large response body, or a very small one, depending on some property of the user. And here's an example of that. This is a WordPress administrator dashboard. Now, if you visit the admin URL and you're not logged in, you will get a simple page like this asking you to log in. It's just a login form, and there's not much else on this page. So the response body in this case is fairly lightweight. Let's say it takes about 750 milliseconds to load. However, if you visit the same URL while you are logged in, you will get a completely different response, and it contains a lot more data than the login form that we saw before. This response body is much larger, and it's fair to assume that it takes a little bit longer to download as well. So let's say it takes 1250 milliseconds to download. So by applying the timing attack on this URL, we can figure out whether a user is logged in to a given site or not. And if you remember those browsing history leaks from before, well, this is actually even worse, because it does not just leak whether you've visited a site or not. It also exposes whether you actually have an account there and whether you're currently logged in or not. This gives an idea of whether you have actively used the site recently. So yeah, getting back to this code example, this is a very simple kind of technique. This is probably the oldest available timing attack on the web. But it's a little bit clunky and crude, and it's definitely not very accurate. And the main problem with this technique is that you're essentially measuring something that goes over the network, and the network is inherently unreliable for any kind of measurement. And this technique measures download time, which does not necessarily correspond to the file size because of gzip compression or Brotli compression and things like that. Of course, it can be made a little bit more accurate by just repeating this technique several times for the same URL. But that means you have to perform multiple HTTP requests, which have performance implications of their own. So in other words, this particular approach is interesting, but not very impressive or scary. And that brings us back to more modern timing attacks. A security researcher named Tom van Hoetem came up with a different approach that is much more robust and accurate. By combining several modern web APIs, he found a way to detect whether a given URL redirects for the user or not. And here's how that works. So first, you get a timestamp. Then you use the fetch API to request the URL that you want to test. To mimic the image-based request from before, you can use these special options. Essentially, it makes sure that you're sending cookies along with the request, just like the user would if they were actually going to request this page for real. The next step is to use the resource timing API to get the fetch start timestamp. This is the timestamp at which the fetch actually started. This makes sense, right? We can then compare this timestamp to our start timestamp that we created on the very first line of code there. And of course, we expect this difference to be super small for pages that do not redirect, because we start the fetch right after we're getting the start timestamp. Now, if the difference is very small, that means it was not a redirect. But if it's greater than 10 milliseconds, or greater than 100 milliseconds, it was definitely a redirect. So this very short piece of code allows us to figure out whether a given URL redirects for the user or not. Okay, but how is that useful? Well, it enables you to figure out whether a user is currently logged into a given website or not. All you need is a URL that redirects to the login page when the user is not logged in, and then you can use that URL to test. For example, if I want to figure out if someone is currently logged in on GitHub, I could use github.com/stars. This is the page that displays all the repositories that you've starred before. If you actually access this page, but you're not logged into your GitHub account, it will redirect you to the login page. But if you are logged in, it will just return the response, and that's that. So in this example, you see that I'm logged into all the websites that you see open in my tabs. So I'm logged into Facebook. What else is there? I think it's Twitter, Reddit, Instagram, GitHub. And just assume that I'm logged in to no other websites than just those that you see there. Now, using that tiny piece of code, it turns out that we can actually accurately detect whether the user is currently logged in to any of those websites. So we tried Facebook already. Let's try Twitter, where I'm also logged in. And yeah, it doesn't even take a whole second for the script to figure this out. The next thing it's going to try is Amazon, where I'm not logged in. And once again, it accurately is able to detect this. By the way, this demo page is online. I will tweet a link. It's in the slides that I will put online later. So you can try this for yourself and see if it works for you. But for me, it got everything right on the first try. Yeah, so another new technique that also improves upon the clunky image-based approach from before is the video parsing timing attack. And this looks something like this. Instead of using an image to download an HTML page, we use a video element instead. And this way, we can listen for the suspend event to figure out when the download has completed. And that's when we start our timer. Whenever the error event fires, it means the browser has parsed the HTML document and realized that it's not actually a valid video file. And at that point, we stop the timer. So the timing difference turns out to correspond to how long it took for the browser to parse the file. And this gives you a very accurate idea of the file size when you use this on different URLs. You can compare the file size like that. So this technique completely eliminates network measurements, and instead it measures the file parsing time. See, because we only start the timer after the download has been completed. This gives you a very accurate idea of how big one file is compared to another, and it's much more reliable than the old image-based approach. Now, another new attack is this one, the cache storage timing attack. It also completely eliminates the need for any network measurements, and it looks something like this. So first you use the fetch API to load the URL that you want to test. Our timer starts after the download has completed, just like in the last example, and before we put the resource into the programmable cache using the cache API. In other words, the script times how long it takes to put this resource in the cache. The longer it takes, the larger the resource is. And the main advantage of this technique is that it is repeatable without having to repeat the HTTP request. You can just download the resource once and then insert it into the cache, let's say 1,000 times, to get a more accurate measurement. So now that we have an accurate client-side timing attack, well, what can we do with this? Just imagine for a second that I work for an evil advertisement company, and I'm trying to find out as much information as possible through my advertisements that I'm serving and my JavaScript that I'm serving about my site visitors without their consent or knowledge. So this is another simple demo. It combines the video parsing timing attack and the cache storing timing attack for optimal cross-browser accuracy. It tries to determine your favorite US presidential candidate based on the people you follow on Twitter. Now, to do this, it makes the very naive assumption that if you follow more people that follow Donald Trump than people who follow Hillary Clinton, it assumes that you are rooting for Trump and vice versa. So when I tried this for my Twitter account, yeah, it correctly figured out that I would actually much prefer Hillary Clinton to be president over Donald Trump. So this is already kind of scary, but it gets even worse. I'm sure you're all familiar with Facebook, right? Well, on Facebook, you can create a Facebook page. And once you own a Facebook page, you can add posts to that page. And what was new to me is that there's actually a lot of tools available to you to fine-tune these posts and to target these posts to very specific audiences. So you can restrict the audience in terms of age, gender, or even the language that they speak. So in this example, I'm targeting my post at people in the age range from 25 to 29 who identify as female and who speak, well, JavaScript is not a language apparently, so who speak Esperanto, let's say. So after creating this post, we can copy its URL and then open it in the browser. And this is what such a post looks like if you happen to match the criteria. So there's the post content, there's also the comments on the post. Of course, in this case, there are no comments, but you get the idea. There's also a list of suggested pages in the sidebar. So let's say adding this page to the cache 10 times takes about 30 milliseconds as measured by our timing attack. Okay. However, this is what you get if you don't match the criteria. The response body in this case is much smaller because all you're getting is just this error message and some links at the top of the page. Now, adding this page to the cache 10 times takes only 15 milliseconds. And this difference in timing makes it possible to actually detect the age, the gender, and the preferred languages of the user using nothing but JavaScript without us having access to their Facebook account directly. And in case you don't believe me, and this is not a theoretical issue, here's an actual demo of that, which kind of scared me a little bit. This demo nicely visualizes everything that's going on as it's figuring out the user's age. So here we're performing 6 different HTTP requests. Each of these requests loads a unique Facebook post that is targeted to a specific age range. Now, then we apply the timing attack by adding each response body to the cache thousands of times over and over again. And this gives us an indication of each response's body size. The largest response body, of course, belongs to the only post that the user can access, and this reveals the user's age range. So in this case, after a couple of seconds, the script already figured out that the victim, well, the user that ran this test, was in the range from 23 to 32 years old. So of course, once we figure that out, we can repeat the process for every number in the range from 23 to 32 to find out the exact age of the user. And here we're performing 10 more HTTP requests, just like before, the same kind of trick. And after just a couple of seconds, it already becomes quite clear, yeah, that the age of the user in this case is 26 years old. So keep in mind that this demo visualizes everything that's going on in the background while it's getting its measurements, but the scary bit is that the visualizations could just as well be hidden. This could all be happening in the background while you're visiting any website whatsoever. You could be reading an article or watching a cat video or playing a game while the website runs a timing attack on you in the background, and there would be no way for you to really know this. This could even be happening in one of the tabs you currently have open in your browser right now. So this is an actual photo of my reaction when I first saw this demo. But believe it or not, it gets even worse, because just a couple of weeks ago, earlier this month, well, it was in August, of course, a new attack named Heist was presented at a major security conference. It turns out that Heist is an acronym. It stands for HTTP encrypted information can be stolen through TCP windows. I'm not making this up. The guys who wrote the paper actually made this up. It's kind of funny, but you know, it stops being funny once you actually read the paper. Here's how Ars Technica summarizes their research. The new attack is capable of stealing social security numbers, email addresses, and more from HTTPS protected pages. That's pretty much a catastrophe for the modern internet, right? Well, and here's what the authors of the paper had to say about their exploits. Heist is a set of techniques that exploit timing side channels in the browser, blah, 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 and they're capable of extracting content like secure tokens from any website that uses gzip compression, which is essentially every website ever that takes itself seriously. And I would like to highlight that the main thing that made this whole Heist attack possible is timing side channels. They're using a combination of different timing attack techniques, all of the techniques that we've discussed today, actually, to pull this off, which is kind of scary. So I think we've seen enough examples of attacks and scary demos. So let's talk about prevention. What can we do to prevent this from happening to us or to our users? Well, as a web developer, there isn't much that you could do. And in fact, when I gave my very first presentation on this topic, it was a much shorter presentation, by the way, there was no real solution for this problem. There was nothing that Facebook could do to stop people from figuring out their user's age by just running some JavaScript. But now I'm happy to say that there is. There is a new web standard called same-site cookies. And unfortunately, this is your only option right now to protect against these attacks. This is a fairly new feature that only recently shipped in Chrome and Opera, and Firefox has already shown interest in implementing it as well. Hopefully other browser vendors will follow suit, and soon we will be able to use same-site cookies and have them be supported everywhere. So how do they work exactly? Well, here's how you set a regular cookie. You basically send an HTTP header that says, set this cookie, this is the cookie name, this is the cookie's value, and then these are the flags that I want to apply to the cookie. You should always use the HTTP only and the secure flags. That's nothing new. Now, if you want to send a same-site cookie, you just append the same-site flag at the end, and you give it a value. In this case, I'm using the value strict. And this causes the cookie to be withheld from any cross-site usage. And this is kind of extreme and pretty hardcore actually, because even when the user follows a cross-origin link to the website, this cookie will not be sent to the website. So for example, imagine that Facebook were to implement this, and I would see a link to a Facebook post on Twitter, and I would click on the link from Twitter, go to Facebook, and I would just get the login form, because it wouldn't send this cookie along. So unfortunately, same-site cookies in strict mode, they break a lot of existing use cases. You cannot even follow links anymore. So I don't think giants like Facebook or Twitter will actually implement strict same-site cookies anytime soon. And that's kind of unfortunate. But it turns out that there's also another value that you can provide for the same-site cookie. You could also use this lax mode. And this doesn't break links and some other common use cases, but it still prevents the timing attacks that we've discussed today. Of course, it doesn't give the same amount of protection as the strict mode, and keep in mind that people might still come up with timing attacks that work in lax mode in the future. So while it's not completely secure and not the best possible solution, it's still better than nothing. So consider using same-site cookies in lax mode. Now, what can you as a web user do to protect yourself against these type of attacks on different websites? Well, you can block third-party cookies. By default, all browsers accept third-party cookies, but most of them provide a setting that allows you to block them. And here's how you would do that in Opera, for example. You open the settings, you just literally search for third-party cookies and hit the checkbox, and there it is. And I would really like to recommend everyone here to try this. Go use your favorite browser, your browser of choice, go to the settings, disable third-party cookies, and just give it a try for a couple of days. You know, if you'll be surprised by how little impact this actually has on your everyday browsing experience. And trust me, if you are, if you are surprised and if you think it's too annoying and it breaks too many things for you, well, just uncheck the checkbox and go on with your life and be attacked by a timing attack every now and then. But really, give this a try, because it's the only way to really be secure against these attacks and against Heist. And with that, I would like to thank you for listening.